Thank
It's
you.
well presented.
Yeah, thank you very much, Professor Han. Hello, everybody. Good afternoon. Very nice to meet you. As ME403, an introduction to ocean engineering and naval architecture. I hope you are all okay with coronavirus. I believe it's going to be over soon. My name is Jinsu Park. I worked in the shipbuilding industry in Korea for more than 30 years. And I retired 4 years ago. Now I'm working on the research cooperation between KAIST and Hyundai Heavy Industry Group. My major was structural design and analysis, and ship is one of the products I was involved in. Today's special topic is hull strength. Strengths of ship structure, the main body of ships. I'm going to focus on the concept. So I'll try to avoid the details. I was told that most of you in this class are unfamiliar with ship and ship in building industry. So I'll try my best to introduce the concept as simply and conceptually as possible. In general, when we are talking about design of some products, for example, ship, there are three main things that we are most concerned about. First, it's performance, like how fast it goes or how large amount of cargo it carries, speed and cargo volume. Second, it's safety. Is it strong enough during its lifetime? I mean, it should be strong enough to endure the possible severest loading. Third, efficiency or economics. It should have good value to make and maintain from a point of cost against the benefit. Generally, these three elements are considered together in the initial design stage and optimized to get the best design solution. Today's topic, hull strength, is related with this second concept, safety of ship structures. Before we get into the subject, the hull strength, I'd like to show you an interesting example of strength test of small structure, soda can, which is probably very familiar with you. However, you may have never thought about its strength. How much weight can this soda can hold? It's an interesting question. Soda can generally very thin, less than 0.3 millimeters aluminum to make it light. But also, it's supposed to be strong enough to act as a kind of liquid container. In this slide, you see two road test situation. The left one is an opened an empty can. The can is vertically loaded and it collapsed about under 55 kilograms. The photo shows 48 at the moment, a little bit after the load reached the maximum. On the other hand, in the right one, this one, the question is, how much load a soda can hold in the unopened and liquid full condition? Actually, this unopened can undergoes many types heavy loadings, like large stack of soda can boxes on top of one another, as you know. Now let's see the test of unopened one.
In aluminum tank, like soda can or space rocket, it's going to be much stronger when there is some pressure inside. So I'm going to say that it's going to be at least twice as strong with the soda in it. So here we go.
Probably looks like much stronger than empty one. How much stronger? Can you guess? Twice? 3 times? Over 100.
Whoa.
Over 200.
Oh.
Over 300. Can you see the deformation ripples in the cylinder part?
Oh, it's going to go!
Oh, ruptures. Showing the deformed shape of the can just before it collapsed. Oh.
That was really nice. And let's see the result. 360 kilograms, so way more. Yeah, that was really nice. And it's failed like really slowly first before exploding.
How much load? It went up to 360, about 7 times stronger than the left one. I think this test shows well the concept of structural strength. You can imagine how the thickness of the can has been determined based on the consideration of many kinds of ultimate loading conditions. Likewise, ship hull strength should be designed to resist maximum loadings by proper design of structures. As you know, the main target in this class, I'm talking about large commercial ships. In case of commercial ships, the main question is how big load or what kind of loading can break the overall ship hull structure. In other words, what type of loadings should be considered for the hull structure to be strong enough and guarantee safety. When we are designing ships, ocean wave is the main external loading. So we usually think about how big wave can the ship withstand, wave height and length that ships encounter during the voyage. are very important and critical to the hull strength. What kind of external waves and internal cargo loadings should be considered? These are the important subjects in the design of ship structures. Ensuring safety in ship's lifetime, for example, 20 years, is the main purpose of designing hull strength. Here are some typical examples of photos showing the entire loss of hull strength, probably as a result of undergoing excessive wave loading, probably big vertical buoyancy force at the center point. These catastrophic structural damages rarely happen during operation at sea, but it can also happen, even though the probability is very low when the ship encounters more serious wave loading than the design wave of lifetime. Basically, ship is designed for the maximum wave loading of 10 to the minus 8 probability. That is the most serious wave among 100 million waves that ship is expected to encounter. Generally, the types of ships are classified according to the kind of cargo the ship carries. If it carries grain, ore, or coal, it's called bulk carrier. If it carries oil, it's called tanker. Container ship carries containers, gas carrier for LNG or LPG. Car carrier carries automobiles. Cruise and ferry that carries people and cars. And warship for battle. The overall shape of characteristics are similar, but the internal structures and functions are quite different from each other, depending on the cargoes and its functions. As you may know, the largest shipbuilding yard is in Korea. Almost half of the total number of large commercial ships contracted last year are going to be built in this country in Hyundai, Samsung, and Daewoo, etc. And most of the LNG and LPG carriers, in other words, high-valued ships, are being built in Korea. When we talk about ship, it may be defined in many ways. In particular, when we limit our concern to general commercial ship, it can be defined as a large watercraft that travels the oceans and sufficiently deep waterways. Also, it carries goods and passengers with specialized missions. By the way, hull refers to the main structural part along the whole ship length, usually made of steel or aluminum. Main loading against the hull waves and cargoes. So hull should be designed to be optimum in terms of low cost and sufficient strength in order to have the proper performance and required strength. By the way, how big is general large cargo ship? Here's a good example showing how big it is. The largest container ship operating in the oceans currently is 400 meters long and about 60 meters wide. It is able to carry about 24,000 container boxes, which are 20 feet long containers. It's so big. More than 50% of the containers are loaded above the upper deck. Actually, it carries a little bit small number of containers for safety, about 20 to 22,000 containers. Nowadays, bigger container ships that carries more containers are being designed in many shipbuilding yards worldwide. I'd like to talk more about hull. Hull may be said to be a watertight body of ship. That is, main structural parts, including cargo holds along the ship length. Hull is supposed to hold many kinds of cargoes and also withstand external and internal loadings. Sometimes top parts of the hull, so-called upper deck, may be partially open in order to manage cargoes. As structural complex, hull is composed of various elements such as plate, stiffeners, frames, bulkheads, etc. This figure shows the inside of typical forepart of the hull of a bulk carrier, which carries grain or coal. Looks quite complicated and composed of many different type of structural members. However, as you see from this photo, the outside of the hull looks quite simple and smooth. This slide shows the typical mid parts of hull structure in tankers. It's also composed of many kinds of structural elements, plating, primary members of web frame, girder, secondary members of longitudinal stiffness. Most of you are not familiar with this terminology, but it's okay. In general, sectional shapes and arrangement are similar along the whole length. Sections are similar. In other words, they are repeated at regular distance of several meters in order to be effective in manufacturing. To make a whole ship, quite a number of these blocks are transported in a certain place as you see in this photo, and assembled together in the place of so-called dock. For your reference, here is a summary of shipbuilding process, which is roughly saying contract, design, construction, sea trial, delivery. The whole process usually takes about 1.5 years. Among them, the construction process for the ship hull can be described as steel cutting, block fabrication, and the block assembly at the dock and ground, and then commissioning and outfitting at the quay on the water. This photo shows a big shipbuilding yard where you probably notice that bulk carrier and container ship are being assembled together in a large dock. In the other dock, you can see 3 ships are being built in the same dock. This one, and this one. I mean, the dock in the shipbuilding yard is very large in general. At this point, I'd like to talk a little bit about basic concept of structural strengths and safety. Here is a photo. 2 persons are crossing a bridge. At first glance, I think the bridge looks quite dangerous. You may wonder if it is safe or not. Is the bridge strong enough or weak? In order to answer the question, in other words, in order to think about safety and strengths of the bridge, we first need to, have to consider all of the loadings that can happen in the bridge lifetime. Whether it's safe or not primarily depends on the loadings, such as weight of the persons crossing on the bridge, number of people crossing together, their walking speed, frequency of crossing, wind force, wind direction, and the current state of bridge condition, etc. After all, the problem of strength and weakness is the problem of the relation between structure and loadings. Loadings are too severe and heavy, structures become not strong. It becomes weak. So designing structure eventually means determining the size, thickness, arrangement of the structural components based on the design loadings for its lifetime. In this slide, I'd like to briefly explain the design concept of hull structures. Basically, hull is designed to be structurally safe and functional in the lifetime of about 20 years, sometimes 25 years, under maximum wave loading, repeated small and medium-sized wave loading, various kinds of cargo loading, many accidental loading, such as slamming impact, collision, grounding, etc. I'm going to talk about those loadings in more details later. From a point of failure, hull structure should be designed properly so that cracks, buckling, and fracture do not occur during the lifetime. Usually, the largest wave loading condition happens under this sagging wave, like this figure. The mid part of the ship bends down, both ends up, and also repeated cyclic loading may continuously happen by encountering repeated small waves at sea. The main external loading against the ship is wave loading. In reality, there are so many kinds of waves that we meet when we sail at sea. From design point of view, we assume that a ship encounters about 100 million waves in 20 years. Some waves are regular. The shape of wave height and length is uniform, like this figure. Some waves are irregular. Wave profile is not uniform, but changes all the time, like this figure. At the bottom, this figure. In terms of wavelengths, there are so many different lengths of waves. As you can see, some examples in this figure. This red color shaded situation where the wavelength is about the same as ship length. In this condition, the maximum, that is the worst wave bending moment, occurs. And also continuous cyclic loading is also applied by repeated irregular waves, sometimes causing to fatigue cracks. I'd like to add some more about bending moment, especially a case that bending moment becomes maximum. The total bending moment can be divided into static and dynamic components. The static is due to cargo loading along the ship length, and dynamic is due to wave load. In sagging condition, the center part goes down and both ends go up. In deflection, maximum static moment happens when the center cargo hold is full. The other cargo holds are empty, like this figure. The maximum dynamic movement happens when the ship encounters a wave whose length is about the same as the ship, as I mentioned before. And when ship is laid on the wave like this figure, the two top position of wave is located at both ends of the ship. That is so-called sagging condition, our most concern. Compression at upper part, tension and lower part. The worst condition occurs, unfortunately, when these two maximum static and dynamic situation happens at the same time. This is one of the cases that the designers are most concerned about. Here are some photos showing possible situations that ship experience in rough sea waves. Basically, ship hulls are supposed to be designed to withstand the wave loadings even in such storm. Sometimes we can expect ultimate loadings due to bar flare impact or bottom slamming or quite big wave height. So most of the time during the voyage of the ship, sea states not so severe, but we cannot evade the ultimate loading. Eventually, we meet these severe conditions. So hull designers always think which is the most critical and the most severest. Next topic is weak areas in ship structure. In human, our body, what part do you think is the weakest? Of course, varies a lot from person to person, but we may think that waist, our back, is the part we feel many troubles, especially we get old. Likewise, the mid part of the ship, in other words, upper deck and bottom plate or midship in the middle of the length, are the weakest area in general. At mid part, maximum bending moment applied, inducing maximum stress. Sometimes structure resulting in structural failures such as cracks or buckling. Cracks maybe initiate, grow in time slowly, and finally becomes final effect. Sometimes large stresses maybe induce plate and beam to buckle locally. I mean large deformation. The buckled shape becomes larger, so-called post-buckling, and reaches final collapse. So hull design criteria should be such that cracks and buckling do not occur during the lifetime of the ship. For this purpose, hull designers should determine thickness and arrangement of plates and many structural members. This right side figure shows a hogging deformation of ship under a big hogging wave. A middle part bent upward. Stresses in upper deck are tensile, very high, red color. I mean, elongation happens, possibly inducing cracks. By the way, very high stress in bottom. They are compressive, blue color, possibly inducing buckling by compression. In ship structures, the most common structural failure is cracks. Crack may be defined as a very narrow gap between two materials. In this case, a separation of material in steel plate or beam, frequently at the welded joint. Cracks may occur at the weakest point and propagate across the deck, bottom, and any place at stress concentration areas, such as bracket toes, welded joint. Once a crack happens, generally it keeps growing into a long size because ship keeps undergoing continuous cyclic wave. In this photo, you can see an example of crack growth at the deck as long as about 20 meters, almost across the upper deck. In these figures, there are several sketches showing typical location of stress concentration. such as foundation of crane, post, hatchcombing, and the bracket, edge of manhole, many kinds of appendages on the deck. Another type of most common ship structural failure is buckling. Buckling may be defined briefly as structural instability, such as large lateral deformation occurring under compressive loading at plate panels or stiffeners. Sometimes panel and stiffener together. A typical example of plate lateral buckling mode at compression shown in this figure. In general, once buckling happens, post-buckling that is much bigger subsequent lateral deformation follows, sometimes causing to final ship collapse. For example, under hogging moment, the highest point of wave is at the center of the ship, and the hull structure deforms center up, percent down. This mode naturally induces bottom structure compression, may possibly cause a buckling at the plate and stiffener. As you can see in this simulation, stiffeners bent this way and that way, plates deformed up and down, red and blue. It's interesting to see a bunch of adjacent plates undergoing buckling together. Sometimes we carry out full-scale buckling test in order to confirm the simulation results. The purpose is to determine the adequate size of plate thickness, stiffness size for buckling not to occur during the ship lifetime. In this slide, I'd like to talk about section of ship, the shape of section along the ship. Design of section is very important because it determines the rigidity. Rigidity is sectional property closely related to hull deformation. That is the deflection of the hull. It depends on the shape of section. The bigger rigidity, the smaller deflection occurs. Here are very simple examples. Beam section A, B, C, D. Area are all the same. The shape of beam A stronger comparatively against the vertical bending, but it's weak to lateral bending, maybe weak to torsion. The way beam B weak to vertical bending. However, beam D very effective for vertical, lateral, also effective for torsional moment. So it's called closed section. So the basic concept when designing hull sections is to make it closed section as much as possible. If we need opening, we make the opening as small as possible. This photo shows a typical block of tanker ship in a shipbuilding yard. It's a part of midship. Can you see a big closed section? Also, several small sections inside the big closed section. This kind of closed section is generally very effective against hull gutter wave loading applied in many different directions. Here are various sections of ship, oil tanker, two big closed section in a whole section. Car carrier has many decks inside, so it's very effective vertical and lateral rigidity. Bulk carrier, center cargo hold, and two side ballast. I mean, three big closed sections. Next, container ship. Container ship has to have big opening on the deck inevitably. So in this case, the thickness of plates for the smaller closed sections should be increased to maintain the rigidity of the overall section. LNG carrier is similar with container ship, a big opening on the deck. So design of sectional ship is very important. In this slide, I'm going to talk about basic knowledge of strength of materials. Some of you may be familiar, maybe not familiar with this. In general, we use the concept of stress and strain. Stress, sigma, is defined as force divided by area. Strain is defined as elongation divided by original length. And the relation between stress and strain can be expressed linearly or non-linearly using the constant of Young's modulus E. Or sigma equals E times epsilon. So this graph shows the typical behavior of stress and strain for structural steel. If you apply force, stress begins going up linearly until it goes up to some limited level. We call it yield stress. Beyond this limit, we cannot apply more force. Instead, elongation keeps becoming large, and finally it comes to fracture. Beyond yield limit, materials cannot resist more force. So when designing some structures, we need to determine the thickness, the size of the stress to be less than this yield stress. For example, about 90% of yield stress. If you continue applying force, elongation increases and becomes too large, finally goes to sudden rupture. In this photo, you see some standard specimens to test material strength in the test machine in the lab. Let's see, simulation of stress and strain. If you apply force, increase it, stress goes up. And it deforms linearly in the first linear stage. If it reaches yield stress, it shows non-linear deformation. It keeps yielding, not showing more increase of stress. In complicated structures, for example, like this figure, as some Ascot area where stress is big comparatively, this kind of high stress and strain behavior generally happens. High stress generally happens under various loading conditions. So finally, cracking failures occur at these stress concentrations. Normal stress and strain are usually happening under Stress and strain. Stress, we can say it's a measure of external resistance of material to external force. There are two kinds of stress, normal and shear stress. As shown in this figure, it's induced from elongation force. Shear stress results from twisting force. Likewise, strain is measure of deformation produced by the influence of stress. So basically, all of the complicated deformation is decomposed by these two types of strains, normal and shear strain. At this point, I think we need to talk about beam theory. Simple beam theory in order to evaluate stress and in a simple beam by bending moment. It is because the whole structure of ship can be regarded as a simple beam. So in this theory, maximum bending stress is calculated by this simple equation, a simple beam theory. You don't need to know it in detail. Anyway, in reality, ship section, actual section is very complicated. So ship designers has to have determined a simple beam property from these complicated structures to apply the material property. Next one is in the initial design stage, we usually use simple beam calculation to determine maximum bending stress and midpoint using maximum vertical and horizontal bending moment. In this case, maximum bending moment is determined, this one M, empirically based on probability approach and some formula by given classification rules. However, in later detailed design, we carry out a very complicated finite element analysis for evaluation stresses at every part of whole structures. In this detailed analysis, we apply actual variable pressure loadings over the whole ship outer surface, considering ship speed, wave height, wave angle, frequency, also internal cargo. Next one. Let's skip this one. Running out of time. Here are some examples of structural failures the ship can experience in operation. Crack that occurs at upper deck, growing to final fracture. Crack at bracket toe of longitudinal stiffener below upper deck. This one is upper deck. Crack at side shell, which probably initiated from this internal structure goes outside. Sometimes we may see buckling at side shell plate. From now on, I'm going to discuss loading situation against the ships. First of all, weight and buoyancy. As you all know, ship float on the water because weight and buoyancy are equal. So vertical equivalence is maintained. Therefore, if weight or buoyancy change, ship comes to move to make another equivalence. In actual voice, wave height usually continuously changes. In other words, dynamic wave loading keeps applying to her structure. So ship inevitably and continuously keeps moving. Here I summarize main design loadings. As Hurlbutter loadings, there are vertical and horizontal bending moment, torsional moment, Hurlbutter shear force. As impact loading, there are bar flare impact, bottom slamming, collision, grounding, explosion, and the various kinds of cargo loading also. Sometimes a vibration and temperature may act another kind of loadings. Now, here is a good video showing wave loading and ship response. Now let's see it.
A simple understanding of the strength and forces acting on a ship's structure is also important. An optimal ship structure has the minimum amount of steel to provide the strength and stiffness necessary to withstand the full range of internal and external forces exerted on it, from sources such as the light ship weight, the weight of cargo, ballast, fuel, etc. And of course the harsh sea, marine environment, the movement of the ship and vibrations. The hull may be compared to a simple beam. When a force acts on the beam, it bends and stretches in accordance with the magnitude of the force and the strength of the beam. Loads generate vertical static forces in still water. Waves generate dynamic forces that act vertically, horizontally and transversely, also creating shear and bending forces, in addition to tension and compression. Longitudinal forces will be experienced in the bow due to a head seas. So at sea, the ship's hull is continuously being exposed to a large number of forces coming from practically all directions. The same simple beam principle also occurs in complex combinations inside the ship's structure, where plating, frames, stiffening, girders, panels and brackets are built up from many separate small beam elements, all working together. Due to the many and variable forces acting upon them, these elements may partly fail and develop cracks and damage in critical areas, causing a serious reduction in local and overall strength. In addition, aggressive corrosion that is found when placing steel in the marine environment ruthlessly weakens the steel and its welded connection.
Sure, it's very useful. The first one is a vertical Hurlbutter bending moment. As I mentioned, it's the most important loading in designing ship structures. I'd like to skip the details. Most of them were touched before. Next, second loading is horizontal Hurlbutter bending moment. First, I'd like you to see a video. Motion simulation under this side direction wave. A big regular wave is coming from the right side of the ship, and the ship begins to move into a rolling motion. Under this situation, generally horizontal, sometimes called lateral. Lateral bending moment is induced with large rolling motion. Moreover, this horizontal moment is coupled with vertical bending moment, so stresses at the upper deck corner may become seriously large. Sometimes, rarely though, it causes ship to suffer from entire loss of stability and final capsizing. This photo shows a large container ship undergoing big side rolling with the side coming waves. Another important Haragata loading is torsional moment. Torsional moment and its subsequent torsional deformation usually happen in oblique wave conditions. In other words, the ship encounters a wave coming from 45 degrees against the course of ship. In this situation, water depths at right side and left side cyclically change. So this difference of the water depths at both sides induces torsional movement continuously and cyclically. In general, torsional Hölgada movement is very critical to container ships because there are big openings on the deck. Another type of loading against ship hull is impact loading. When ship sails under head sea, wave coming from the front, wave direction is about between 0 to 45 degrees. Impact loading may happen on the bow flare, depending on the wave height and speed. Bow flare is the front structure above the water. In this area, impact loading may happen, cause permanent yielding deformation. So you can see in this photo an example of yield deformation. For the research of design bow flare impact pressures, model tests are sometimes carried out using pressure sensors installed at several points. And we sometimes perform ship motion simulation, considering both ship structure and water around. You may notice high pressure, red color here on the bow flare. Another type of impact loading is bottom slamming. This loading case often occurs at high-speed ship, and when the ship is sailing in head seas, moving vertically in pitching motion. As you see in this simulation, when falling downward from the vertical motion, very high impact pressure occurs over the front bottom area. Sometimes it causes a permanent yielding and fracture. Even the bow flare impact, bottom slamming, local loading also induces another type of high frequency Hölgada vibration, so-called whipping, and resulting in the extra vertical bending moment. One of the loading conditions we need to consider is collision, especially oil tankers and gas carriers. We often hear about an accident of ship-to-ship collision, as you see a case in this photo where a large bulk carrier collided into smaller oil tanker. You can notice a big spillage of oil over the large area around the ships. So designers need to evaluate strengths of side structure. In general, it's very hard to test using a full-scale actual ship. So many numerical simulations often carried out to evaluate side structures, considering colliding speed and shape of the front part of colliding. This figure shows finite element analysis models of large oil tanker and LNG carrier. In this analysis, very large displacement, nonlinearity evaluation, and plate, in this part, plate ruptures are included to analyze collision penetration. Another type of accidental impact loading is grounding. Grounding impact rarely happen accidentally when the ship runs aground or make contact with the ocean bed, such as rocks. Main point is to properly design the double bottom structure for liquid cargo oil. Liquid cargo not spill out of cargo hold. For this purpose, a numerical simulation for the double bottom against grounding is often carried out. In this simulation, a nonlinear plate tearing analysis is included. Last one, another type of special loading is explosion. This case is kind of limited to warship. You may imagine many scenarios of explosion near or inside warship. Warship structural designers should understand the ship structural response to underwater explosion impact, because they need to carry out proper reinforcements to minimize the casualties and damages. For this purpose, real explosion tests may be conducted, but most of the cases are evaluated using technology FSI, fluid structure simulation. In this simulation, ship structure, a large volume of water around the ship, and the explosive are included in the simulation modeling. And generally, it takes a lot of time in calculation and also needs very highly skillful experiences. Thank you for your attention. I hope this class could have give you more understanding of design, concept of and strength. This slide shows a ice-breaking ship. We call it icebreaker. There's very special functions in front of it. Yeah, thank you very much for your attention.
Thank you very much. It's question time. Any question from student? One question from me is, can you provide this presentation slide to student later?
Yes.
Thank you. And I can. Oh, Xin can write Korean character too.
Korean, okay.
No more questions? All right. Then we can close this class earlier, and hope you have enough time to prepare the Thursday presentation. Right? Thank you very
Thank you.
much, everybody. Thank you, Professor Park.
Thank you.